Welcome, everyone. I'm James Ward. Thanks for coming today. So, does anybody remember the original vision for Java? It was going to run on your refrigerator. It was going to run on your ring. It was going to run on cards. It was going to run coffee makers everywhere. Who all remembers that? Yeah. So that was fun. That didn't really work out. Now this is what we do: is we put Java into containers and put it on container ships and sail it across the ocean. So things didn't quite generally work out the way that they were originally pitched. But a lot remains the same for what we're trying to do, is have portability across environments. So that's what our talk is about today, is even in the world of containers, how do we write once and deploy everywhere from containers to serverless? So yeah, I said, I'm James Ward, work on mostly MCP stuff at AWS. And then I have with me Matthew.
Hi everybody, I'm Matt. I'm the modernization team here at AWS, so I spend a lot of time working with customers on things like serverless, containers, Kubernetes, etc.
Awesome. Okay, so today we're going to dive in, talk about how we can have this portability that we dreamed of our Java applications, but much more server-oriented. So let's start with the why. I always like to start with like why in the world would we need portability? Why does this even matter? So at the very minimum, we typically have at least a few different environments that we need to be able to take our applications and run them on that are different. We've got local dev, and that can be, maybe you're using dev containers, maybe you're using other things to run, but you've got your local dev place where you're going to do it. Maybe it's up in the cloud, but still essentially local dev. And so that's an environment that your stuff needs to work on. And then you may have a place where you're going to run agents and work with agents. And we'll talk about AI agents and agentic execution, but now we have these agents that are being able to run our application, make changes, run the test, whether it's like Junie or ours is from Amazon is called Q. That is yet another way that our applications are being run and interacted with. And we've got CI/CD. Hopefully you're doing CI/CD, and that becomes yet another environment. And then maybe we have some type of like light production that we can spin up just to make sure that, all right, networking is going to work. Those sorts of the things that are kind of near production, that's going to work. Developer sandbox type of environments. Staging, integration, and production. So lots of different environments usually in our complex systems. And all of these different environments have subtle differences and have different ways that you do configuration. And so ultimately, even though we've got containers and we've got a JVM that runs everywhere except for on my refrigerator, we still have a lot of pain with how we move between these different environments. And so that's what we want to talk about is kind of how can we reduce some of that pain. So containers, they're great, but they don't reduce all the pain. There's still some challenges there. There's things like how do we deal with external services, configuration, networking, sidecars, service discovery, monitoring, security, feature flags, all sorts of different things that lead to this pain of moving between these different environments. And so we want to cover some of the kind of tips and tricks and ways to think about how we can move across these environments and have portability better. So before we go on to some of the kind of operational aspects, I wanted to talk a little bit about packaging because for me, I've used Jib and build packs and Docker files, and there's some trade-offs between all these. I guess that most people here are probably using Docker files. Is that right? Yeah, a lot of Docker files. And that's fine. You can use Docker files and you have a lot of control. Build packs, we'll see in a little bit. That's something that came out of Heroku and the Spring folks have gotten behind, so we'll talk about build packs and see that in a little bit. And then Jib is from Google and integrates directly into your build tool, Maven or Gradle. And doesn't require a Docker daemon is one of the nice things about Jib. And then build packs runs in Docker daemon to do the build. So just some different trade-offs there. I think generally my favorite one of these, not universally, it kind of depends on some situations, but generally my favorite is build packs. If you've ever used Heroku and just do git push Heroku main and have done that deploy experience where it just detects like, oh, I see that you've got a Gradle build or an SBT build or Ruby the application or whatever it may be and just detects that and then does the build. That's the magic of build packs, is being able to detect and then build into the runnable version of the application. So I work with a lot of different languages and technologies, and so because of that, build packs, because of its kind of universality of being able to build anything, I use that a lot. But yeah, some different trade-offs there. Okay, so that's on the kind of building container side, some different options there. So let's talk about the different environments, and I'll hand it over to Matthew to get us kind of oriented on the different environments that we're going to be diving into today.
Sure. So I think, we first start building stuff locally, so we've got to think about how we're going to build on our laptops when we get started. So we could use the local JVM. We might have a Docker container. We also, we can deploy to a whole bunch of places. And when we're starting a project, we don't know. We shouldn't know. We should leave our options open. So we might want to be deploying to some sort of serverless config. Maybe we're deploying to Lambda or Fargate. Maybe we are running on some sort of containers orchestrator. We want to deploy on Kubernetes. And so we want to think about how can we manage all these environments and give ourselves as much freedom. And then when we're thinking about that local environment, really what we're trying to optimize for is how can we get really, really fast feedback? How can we write codes and as quickly as possible understand if we're heading in the right direction? So as soon as we type a property, we want to know, does it exist? We want the red squiggles in our IDE. We want then, as soon as we go and save that file, we want to automatically go and automatically build it, go and get some feedback. Is there any compile errors? We want to make sure that our app preview is loading, so we want that as soon as possible. Maybe we'll wait a few seconds, but more than a few seconds, and our short-term memory is starting to forget what we're doing. We want to be able to run some sort of integration test whether it's actually connecting to the database, whether it's working with some of the other services that make up our distributed application. Here, maybe we can wait 10, 20, 30 seconds for that, but much not longer than that, and then suddenly that's becoming a frustration as well. I really think that's the primary goal. It is about how can we make it as easy as possible to problem solve, to work on an application. And actually, as a kind of secondary goal, important but maybe less so, is when a developer onboards, can they get started in 10 minutes? Can they get started today? Does it take 2 weeks? And when we deploy it, is it consistent? Is the database consistent with what we're using in the cloud? Are we going to see these kind of integration issues as we start to go through our environments? So I said, we want to keep our options open of where this stuff runs once it gets into the cloud. So if we think about, fundamentally, we've got an application running on our laptop. We've got something running on an operating system. We've got our JVM that's running it, and then we've got our application code. We've also got some other stuff that's part of the stack. So as we get to the cloud, we suddenly want to think about having multiple copies of our environment. We want some redundancy. We want the ability to scale. We want to be able to route traffic to the appropriate compute. So we've got a load balancer. And we want to think about how we're going to scale it. So we've added an auto-scaling group. And we've got some sort of pipeline that when we commit into the appropriate branch, it's gone and delivered it. And so the kind of nearly 20 years ago, 19 years ago, Amazon released this thing called EC2, and it's great. We're going to take care of undifferentiated heavy lifting. What that really means is we're running a data center for you, which has got a hypervisor on it. But you're still running that entire stack in the cloud. So you're still having to think about your operating system, patching that. You've got your JVM, you're responsible for that. You've got all of your app dependencies. You configured your load balancer, you configured all of this stuff, you've got some Jenkins boxes running your CI/CD, and you're paying for all of this stuff. So you're paying for it at midnight when no one's visiting your application, you're paying it for all of your integration environments. But we are taking care of that hardware for you, and that is useful work, so a benefit for customers. But like James says, as much as James Gosling wanted the JVM to be the unit of portability, containers happens, and everyone thought this is awesome. Let's Docker everything. And that enabled us to optimize this a a bit more. So now we can have our app and our runtime and our dependencies running in a container on a shared operating system. So we're not running multiple copies of this operating system. It enables us to pack our applications more tightly into our VMs. We need some way to work out how those applications are going to run and scale and where we're going to place them in our architecture. So we need some sort of orchestration agent and a container orchestrator. When people started doing containers in the cloud, they were running all of this themselves. And it's relatively complicated, and AWS is on this journey. We want to take away undifferentiated heavy lifting. We want to start doing the stuff that really isn't business value. Is there business value in having a really slick container orchestrator? Probably not. So we took this on and launched ECS, so 10 years ago this year. Actually, if you're using Kubernetes, it's exactly the same model. So the Kubernetes EKS model is, you run your EC2 instances, you run your containers, we run the control plane and some of the plugins for you. And you're still running the rest of the stuff, and you're still paying for those provision resources. So you're paying for a bunch of hosts, whether or not they've got containers running workloads in them. It's on you to optimize and pack efficiently and scale up and scale down. So a couple of years after ECS, we released something called Fargate. That moves the shared responsibility model. So we start taking on responsibility for the operating system. We're now running all of the agents that are running on those EC2 instances that allow us to orchestrate a containers platform. You're still responsible for your kind of load balancers and your deployment, but it also changes the cost model. So now you're only paying for the containers that are running. You're not paying for the whole EC2 host, whether or not it's running a container. And launched at reInvent last year. We've got auto mode for EKS. That's also in the Kubernetes ecosystem. We're also on that journey where we're starting to do more for you. So this is a model where we look after and patch the underlying EC2 instances. It's not quite the same as the Fargate model, so you still pay for the whole EC2 instance, but we're taking on more of that shared responsibility. And you should expect the kind of direction of travel is that over time we're making these things more and more serverless. But I think there's a few jokes there about all the different ways to run containers and applications in the cloud. There's a whole bunch of stuff. I think that largely what these kind of serverless models, we've got the container orchestration models. We also have a whole bunch of kind of opinionated models for specific use cases if you want to run a batch workflow or an IoT application. And it's a minefield. We have got some documentation about working out which is the right one. But everything's becoming more and more serverless, and even Kubernetes is becoming more serverless. But the original serverless service was Lambda. So that's 10 years old this year. I thought it was interesting that kind of James Gosling had this vision that the JVM would be the unit of portability, and in fact what happened was containers became the unit of portability. Lambda spent the last decade in a kind of parallel universe where actually the VM, the original unit of portability, the virtual machine, is going to stay the unit of portability. And that has some really interesting different trade-offs. So one of the challenges with a container is that you're in a shared space, you're on a shared host. So it's really, really difficult to do multi-tenancy. It's very difficult to securely run different customers' code on the same box with any degree of protection, and largely those models haven't worked. So you end up in some way having to pay for spare compute. If you can get stuff into a VM, that's great. We can start to really tightly pack customer code onto a bunch of different hosts and have some different performance characteristics. In order to do that, we have to innovate a whole bunch around VM technology. So we invented something called Firecracker. Firecracker is a micro VM that has a very, very low performance profile. We can start up a new VM in less than 100 milliseconds. Super, super cool. And that allows us to do something kind of different. So we go from a data center world, we're going to go and build some compute, we're going to do some resource planning for the year, and we're going to hope that we don't go over that in our seasonal spike, because it might take us weeks to get more hardware. We've all moved on from that. That's great. We can move to a container model where we can start adding and removing new capacity. It probably takes tens of seconds. Actually, with a reasonably large Java application, it probably takes minutes to add more compute. It also means that we because it takes minutes to start stuff up, we can't scale to zero. So we've got all these different environments that James was talking about, dev environments, staging environments, sandboxes. They're all sitting there on some baseline level of compute, whether or not we're using, when everyone's in bed, and it takes us a little while to spin up. With the Lambda model, because we can add sandboxes in just a couple of seconds, in fact, we can add 1,000 sandboxes in 10 seconds, ready to run your code. It means when you're not using it, we can switch it all the way off, and we can go up to these crazy spikes when traffic comes in. Just to give you an idea of how fast that is, we had 1,000 execution environments every 10 seconds up into your account limit. Each of those execution environments can have 6 vCPUs, 10 gig of RAM. So like in a few seconds, you could basically get a supercomputer that you pay for by the millisecond. So super neat. As well as this like alternative universe where VM is the unit of portability, we've also got a universe where HTTP isn't the route into your application. So we wanted to go and reinvent that. And actually, the way that you go initialize an application on Lambda is we take an event, we serialize that event a bit of JSON, and we send that over to your application. So that might be a change in state. It might be something that looks a lot like an HTTP request. So it might come from a load balancer or an API gateway or a function URL. And there's a whole bunch of flavors of them. They all get serialized into JSON that looks like an HTTP request and sent to your application. And it goes into some work, and there's a bunch of different operating models for it. It might be a synchronous request response. It might be asynchronous. The kind of really interesting one that not that many people know about is this poll-based one. So if you want to process events from something that's a poll model, maybe something like a Kafka stream, and the Lambda service runs a durable polling fleet that automatically scales up and down, listening for those messages. As soon as there's a batch of messages on your stream, it will send them to your application. So for kind of really, really important low throughput streams, it's a super cost-effective, really powerful way of doing it. So what that looks like in your code is that we've got an event, we've got an API gateway event that deserializes that piece of JSON. There's actually a different event for a V1 and a V2 and a function URL and an ALB, so they're all slightly different objects that you have to think about. We want to go and run some business logic based on stuff coming into an SQS queue. That's got an SQS event, an SQS batch response. S3 event has hundreds of services that will all integrate with Lambda. Basically, all the major services on AWS will integrate. They've all got a signature. We provide you an events library to do this, but suddenly that code doesn't look super portable. It's like we're tightly coupling our business logic to the thing that's triggering those events. And a lot of the applications that we're doing, the web has won out as this model for how we build things. Maybe everything will be agentic and MCP tomorrow, but today the web is the main thing. So actually, a lot of the time, what we're doing is we're serializing things that look a lot like HTTP responses and sticking them into a functional model that's running synchronously. So one of the ways we can make this more portable is Spring Cloud Functions. Spring Cloud Functions is super cool. So it still maintains that functional model. Something happens and we're going to run some business logic code. But it starts to abstract that away, so it gives us some more routing and mapping. It abstracts away a lot of the kind of interfaces that are part of the AWS event library. So it makes it much easier to kind of compose these things together. And I want to move this function here from being triggered by an API today to being triggered asynchronously by a queue tomorrow, and I want to chain these three things together when some event happens. So a super neat way of doing it. Really, really useful. However, if you're building Java applications, certainly Spring applications, most people are writing more traditional MVC applications where we've got REST controllers. When we're running them in containers, we're almost certainly running them here because we don't have that evented interface. So can we run them on Lambda? And of course, the answer is yes. What we need to do is we need to have some sort of adapter layer that takes all those different kind of JSON serializations of HTTP requests and responses, do some adapter logic, and pass it through to our framework. So we've got a project that I've done some work on, which is called the AWS Serverless Java container. That's basically a serialization library, does that adapter layer, plugs into most of the common frameworks, so things like Spring or Micronaut have their own implementation, or Quarkus. And essentially what that does is we take, in a Spring world, we'll take the AWS events, we'll convert them into something that Spring Cloud Functions can think about, and then Oleg and the team on Spring Cloud Functions then take that event and they pass that to Spring Boot, and then it all works as a normal kind of Spring Boot application where we use that controller syntax and all the responses are mapped, all of the HTTP response codes are respected, so it works pretty seamlessly. So, that's great. I can take an application that was kind of running locally in a build pack and deploying it to containers, and I can run it on Lambda without having to make some changes. Like, why should I bother? I think that if I think about where we use them, if you've got an application that's in production today, you really deeply understand the traffic pattern. You can optimize for it. Containers are a great place to run that. If it's something new and you don't know what the traffic are, or the traffic's inherently spiky, that's a great fit for Lambda. There are a whole bunch of applications that are just never going to run on Lambda. Your 20 million line monster application, don't run it on Lambda, but kind of modern APIs, event-driven stuff runs great. I also like the idea that if it's something that's evolving, where you just don't, I'm getting started on something today, I don't know what's going to happen, let's run it on Lambda. And just to look at the kind of tangible cost for this, I took a kind of basic Spring Boot application, did some testing, and ran it on a Fargate container and ran it on Lambda. And what I'm calling a low traffic example, just still into millions of requests a month. It's about 7 times cheaper to run that application on Lambda. And I've seen customers have taken applications that with a whole stack, all the environments between dev environments, multiple dev environments, customer test environments, have been tens of thousands of dollars a month running on EC2. Tens of dollars a month on Lambda, so 1,000 times cost saving for lots of these long tail applications. Of course, it's not the whole story. Like, stuff depends. There's trade-offs for all these solutions. Once we start to crank the volume up on this and we get to something like 10 million requests a day rather than a month, we're starting to see that point where we're getting to a tipping point. I think where the tipping point is a lot higher than where people think it is. So here we're just starting to see Lambda become more expensive than the equivalent workload on Fargate. $100. Is it worth the operational overhead of taking more at that point? I don't know. But maybe you start something on Lambda as a startup, you become a decacorn, and you've suddenly got millions of customers and super high traffic. You want to make sure that you've got an exit path that you can move away from your Lambda model to something where you can super optimize, and you're maybe running on Kubernetes with Spot, and you've got a platform team at that point. And that's a great story. So we want to protect ourselves from the kind of trappings of success. So that's a whole bunch of theory about how these kind of models work. I'll hand off to James, who's going to
we'll walk
put some of it to demo.
Before we do, does anybody have any questions for Matthew before we go on to a demo? Anything that's burning questions? Can't quite see everybody. Yeah, go ahead.
Yeah, so I think that's a great question. How many should you have a Lambda function for every API endpoint? And I think that's a common misconception. Certainly with the kind of the model that I was showing with Java Serverless Container, a Spring Boot application, you could have a dozen, even 100 endpoints served by a single Lambda function, and that's absolutely okay. I would be thinking about how do I split them into Lambda functions in a similar way that I would be thinking about them in containers. What's the deployment frequency? Are we bundling together a set of APIs that are owned by a single team? You're having those in one or a handful of Lambda functions makes sense. I've also seen some interesting stuff around kind of CQRS patterns. So maybe you have all of your read Lambdas, all of the kind of read endpoints in one Lambda function because they have a particular kind of performance characteristic and they're heavily cached, and you have all of your kind of write and delete Lambdas in another separate Lambda function that's got a different security model, has cache busting, etc. But I think it's a misconception that you need to have you've got 200 endpoints, you've got 200 Lambda functions. If you go around that journey, it's going to be pretty painful. I'll talk a little bit about Snapstart at the end, but kind of how Snapstart pricing works and that model makes it sort of encourage encourages you to have slightly larger Lambda lifts. I think that the Lambda team calling what we call a Lambda lift a monolith is a bit of a disservice. The kind of Lambda lift patterns we see, which are typically 20 endpoints in a Spring Boot application, the rest of the universe calls them a microservice. On Kubernetes, it'll be a microservice. On Lambda, it's still a microservice. It just happens to have this kind of slightly awkward name in the community.
Good question. Yeah, and I think security, like which roles and stuff, would be a key indicator on like, okay, this Lambda function needs these roles, and we want to keep it as granular as possible. So that would be another good kind of breaking point for how you distribute that. Okay, let's dive into some code and see how some of this stuff all comes together. So at the high level, what I want to show is this idea that if we think about portability up front, then we can actually have an architecture that allows us to easily move between environments and then get the kind of best of the world in the environment that we're in. And so I'm going to start with local dev and local test, and I want to just walk through this application and some of the characteristics of it. But I'm using a test container for my Postgres database. And so one of the things that we mentioned earlier was how do we try to get service consistency? I don't like the idea of using in-memory database, whatever it's called. I haven't used it in a while. I like to have my database that when I run my integration tests, it's going to use the same database for local and for test and for local dev as it's going to use on my production system. And so test containers allows us to do that. Anything that can run in a Docker container, we can throw into a test container. And there's some annotations here that are specifying the kind of life cycle of this container. And so the at restart scope, what that's saying is that when I'm running in local development, keep this container running for the full kind of duration of my JVM. Don't restart it. If I comment out that restart scope, then instead it will, anytime my application server restarts, then it will restart the container. And then there's different ways to control the lifecycle across tests. Let's say you want all the tests in one class to use one instance of the database, or maybe you want them each to use their own instance of the database and run them in parallel. You can configure all that, the lifecycle around the test containers. So I've got my Postgres test container, and then I've got my Spring Boot tests. I have this bar repository, which is just a CRUD repository of bars. I'm not very creative, so I do a lot of foos and bars. So I've got my bars in my bar repository, and then I've got two integration tests here. One is just a test to see if I save something into the database and then query for it, does it work? And then I do another test here to kind of validate that sure enough my database did get reused across these tests and make sure that there's one record in there. So let me start by running the test for this thing and just verify that this all works. So I do have Docker running locally, in this case in WSL, and so it's going to spin up that Postgres container within Docker, within WSL, and then we see, sure enough, yay, my test passed. If we scroll through the logs, we'll see that it connected to my Docker that was running on WSL. It first tries to connect to one on localhost and can't, but then it connects to the other one. Then it goes and starts up my Postgres test container, and all this happened pretty fast with starting up a Postgres container. So even with that, it happened in 110 seconds total. So there was some time in setting everything up, but 10 seconds to do my integration test against my database with the consistency of test containers being the same database that I'm going to use in production. So that's kind of where I'm starting is with tests, but then there's the element of local development, and there's I think a kind of newish feature in Spring that I love because I like to really keep the main part of my application. So there's main and there's test. I like to keep the main part of my application just prod, like things that are only about prod go in main, and anything that's about local dev or test goes in test. And Spring now has this way where in my test Kotlin, I'm using Kotlin here, but obviously it could be Java. So in my test Kotlin directory, I have a main function. So just like you're gonna with Spring Boot have a main function in your main, I have a main in my test, and this allows me now to run this application for local dev with the dependencies that are available in only my test scope. And so things that are in my dependencies in the test scope is test containers, dev tools. I'll show show you the Gradle build here so you can see all of those. But so I've got these dependencies that are only available here in my test scope. And so by having that test main allows me to run this application, run my application with these dependencies available. So I think that's kind of a newer feature of Spring, and I love it because then I don't have to pollute I can keep things real nice and clean, that only the stuff in my main scope is for production, only the stuff in my test scope is for test and local dev. So let's go start up that application. So this is going to be this Gradle task here. So it's called, in Gradle, it's called boot test run. So instead of your usual boot run, it's boot test run, and that runs the main that's in the test scope. So great. So now that starts up my application and should have started up my test container for Docker or for Postgres. So I've the things that were available in here, that Postgres test connection here. This now then gets run when I run local dev. So when I'm doing local dev, I'm getting my Postgres database as well, just like when I ran my tests. And now I can actually go see what this application is doing. Let's open it here in the browser and go to localhost 8080. And I've got my fancy bar storing application. Can put in a bar and save it to the database. Yay, it works. Super exciting application, but it did save to the database. Now here's one of the cool things. Let's go check out our. I'm weird and like to write my HTML in Kotlin, but no matter how you build your UI, if you even have a UI, I'm just going to make a little change to the UI so that we can see that when we make a change with DevTools, it's going to reload. So I'm going to just come in and change this title here. So when I save it, there's two different ways to do it. I can have it run the build, or I can run Gradle in kind of continuous watch mode that watches for files being changed and then rebuilds them automatically. But what we should have just seen there is after it rebuilt the class files for that change that I just made, then Spring DevTools notices, hey, there was a change, and then it reloads the application. But if we go over here and hit reload on the application, we now see the my bars, but the database didn't get reloaded. And so this is one of the nice things with that restart scope on the test container for Postgres, is that even though my whole application restarted, it didn't restart the database, which is generally what I want when I'm doing local dev and doing those iteration loops. So, okay, so that's kind of the local dev story for this application. I think kind of Spring does a great job of making this stuff pretty nice for how we can do this local dev, use test containers. Quarkus has some similar things as well if you're using Quarkus. So, so all good stuff on that. But yeah, other than that, like there's nothing else unique about this setup. It just is kind of putting things in the right place and allowing us to use dev tools, use test containers in kind of the best way. Okay, so that's our basic application. I didn't really even show the code, but all it is a little REST application there that reads and writes bars from the database. So. Super fun. Okay, now let's go into the packaging side of things. So for packaging, I'm going to start with containers. And Spring has built-in support for build packs, as I mentioned earlier. So if I want to get a container for this application, I don't have to change anything about the configuration, the build. All of it's just built in with Spring. And so I can say, Gradle, boot build image, and that's going to build a container image for me. I don't need a Docker file, and it's just going to be like, hey, okay, here's how we build a Spring application and put it into a container, and there we go, all done. So that was pretty quick. And now we can verify it by running that Docker container. So very similar to how we would run it, in whatever container environment we want to run it in. I did have the configuration for my data source externalized, so I do need to specify that. I am running, in this case for this test, just just a standalone Docker container so that I can connect to that. But there we go. There's my Spring Boot application now starting up from a container. And so now we've kind of seen that portability across kind of local dev and test to containers. And obviously we could take this container and run it in Kubernetes or ECS or wherever. But let's just verify that it works. And I think that I had run this before with the same database and put in an ASDF already in the database. But so there we go. That's my application now running from a container with no changes to it between how I did things for local dev and for the containerization. Okay, now that's containers. Let's close that down. Now let's go over to Lambda. So again, this idea of like, if I've built things, if I've kind of set up things in the right way, I shouldn't have to make environmental changes to be able to move between different environments. And sure enough, we can now do that with Lambda. To do the Lambda one, I did have to make I did have to put a few things into the build, but they don't affect the rest of things. They only kind of come into play when I'm using it for Lambda. And so the two things that I had to do to make this work on Lambda, one was that I needed to bring in that library that Matthew had mentioned. Did you build this one? This is from you?
Got a couple of commits.
Yeah, great. Well, thank you for this. So this is that adapter that was mentioned for how we can adapt a Spring Boot application to work on Lambda. And this is just a regular old Spring REST controller application, but that magic little library there is going to do that bridging of the Lambda calls to the Spring stuff and do everything that's needed for me. So I add that dependency in, and then one more little trick. So my other little trick is that you do need to, for Lambda, be able to package this application up. But one little trick is we can't have Tomcat in there, right? Like Lambda comes with Tomcat or something?
Well, it has a whole event model. So your API gateway is going to send a serialized request. You don't need to run a web server in your application.
Yeah.
So we need some way to actually know when we get that serialized request, where do we send it into your application? What's the entry point?
Okay. So we need to get, and if we try to start it with the Tomcat on the class path, it's like, sorry, I can't do that. And so we actually need to remove Tomcat from the class path when we package this up for Lambda. So this is my Gradle way, and there's a couple different ways. I think our documentation says to do it a different way. I came up with this way because I just wanted to use some of the kind of standard packaging stuff in Gradle. So this says, hey, if this is being packaged by Lambda's this thing called SAM, which we'll see in a second, then exclude Tomcat from the class path for packaging. And that was it there. But let's see how that actually comes together and works. What I'm going to do is, I got to show you one more thing, which is our SAM template. So for Lambda, typically, not always, and it's this file, typically this thing called SAM gets used, which is infrastructure as code, which defines everything. And so my SAM template, in this case, it's got my VPC, it's got my subnets, it's got my database security group, my Lambda security group, my Aurora serverless cluster. This is my Postgres database. It's got my actual function, which is my Spring Boot application, the one that we just saw. It has the variables that wire the data source, the Aurora data source and the settings there in. So all sorts of things to define the infrastructure here. But this file actually gets used when I want to build, do the SAM build. So SAM is what's that stand for? Serverless application model. Thank you. So SAM build, we'll look at that file, figure out what needs to be built and how to build it. And it's essentially just going to call Gradle, in this case, to build my application into something that then can be run within Lambda. And so I think that was nothing changed. It had good caching there. So great. So done. Then we can also now take this thing and we can SAM deploy it, which would be one way to actually get this actually running up on Lambda. But we can also run it locally. So there is essentially a Lambda emulator that I think runs in a Docker container. It requires Docker, runs in a Docker container. And so we can run this thing like it's going to run in Lambda. We can run it locally. And this would be good to do as an integration type of test before we would deploy it. And so now I can actually start up my Lambda function, which is my Spring Boot application. And in this case, I had to do some wiring to wire it to a test database that's also running running locally. But there it goes. It's up and running. Let's go check it out. And this is now running either through a proxy, so it's on localhost 3000. But if we make this request, and it's going to connect to the same database, or different database, not sure, different database there, but one of my local running databases. And then we see that here's the logs for the Lambda emulator saying, yep, we started up your Spring application, we connected to that database, and then requests come in, and it delegates those requests through that library so that Lambda can handle them in the right way. So now we've had that portability across local dev and test and containers and Lambda with really not a whole, like no changes to our code, certainly, but also only a little bit of configuration that we needed in our build to do, looking back at it, to do that Tomcat thing and add in the bridge, the container, what's it called?
Java serverless container.
Java serverless container. Yep, that one. So that was the only thing that we had to do. But architecturally, no differences to our application across all those different environments. So, okay, so that's our little demo. All this is up on GitHub. Let me hop back over to slides and get you the link there. So this is in a branch in a repo on my GitHub. The repo is called Spring Boot bars _bars, and then the branch is lambda-web is where all that stuff is. So, okay. Let's see how we're doing on time. 9 minutes. Let's keep moving.
2 minutes. Yeah. 2 minutes for because we were talking about Lambda. Cold starts. You can't do Lambda without talking about cold starts. Why do cold starts matter when we're talking about Java applications? So we've got this different model that takes a VM. A request comes in to the Lambda service. We have to go and download your code. So we've got to go and get your jar file from S3. We create a VM for it. We then start initializing some code. So it's Java. So we've actually got to do some allocate a heap. We've got to do some class loading. If we're in Spring, we've got to do runtimes dependency injection. We give you a CPU boost here, so it's faster than if you're running it on a normal container, which might be a minute. We're getting it down to seconds. But it's probably several seconds, and then an invoke comes in, and hey, it's Spring, so we're still being lazy, and we still haven't done stuff, and we've still got to do more jitting and get this stuff running, and then finally we're ready to execute your code. So that whole process, in a kind of worst case scenario, could be 15 seconds, 12 seconds, long enough to make it kind of not really a viable route to run a large Spring Boot application with 50 endpoints. But the new invokes that come in super fast. So we launched this thing 2 years ago called SnapStart. SnapStart is pretty neat. There's a few tricks to setting up SnapStart. So I thought I'd go and set that up in this application here using Amazon Q. So Amazon Q is our agentic code agent, and I'm using Q CLI so I can interact with Q and get it to run agentic workflows from the CLI without being in the IDE. And I said, hey, Q, go ahead. This is James's laptop, so I don't care what you do. Trust everything. Please don't delete his profile directory. But we're going to trust everything. Enable SnapStart on this project and implement something called function priming. I'll talk about what function priming is in a minute. So I'm going to go and set that off, and Q's going to go off and do some stuff. It's going to take a few minutes because it's going to go inspect the code base, look at a whole bunch of things, go and start to implement that. So what do I mean by SnapStart and function priming? So instead of having a jar that every time a request comes in and we give you a new sandbox, we've got to go and do that whole life cycle. We can move some of that work to the init phase. So when you publish a new version of your application, we're going to go and do some work. We're going to download your jar. We're going to start up a JVM. We're going to get some stuff running. And then we're going to snapshot the entire VM state. We're going to put that in a tiered cache so we can start to restore it really, really quickly. And when a request comes in, we're going to pull down a copy of that cache, stick it into a new VM, resume it, and run an invoke. And so all of the subsequent requests that come through are all going to land from that cache. There's a whole bunch of cool stuff we've done to make sure that they're secure and we haven't got kind of collisions on certificates and GUIDs and keys and things. Those low latency caches, yes, typically we're looking to get under a second. A second is our kind of magical number that we think makes it a viable application. We can dig a little bit deeper and say, what are we doing in this initialization phase? So by default, it's going to kind of get your application running, go and download the jar, start up the JVM, and then it's going to snapshot it. But actually, if we're clever, there are a couple of hooks we can use where we can start to do some additional work that might happen. So we might do some of our stuff that's going to force some lazy initialization of classes. We might also go and exercise some code paths that are likely to be used. So can we connect to a database? Can we hit an API? Can we start to use bits of the CDK? That's going to put them through the C2 compiler and get them jitted and ready to go. And then we can snapshot it. And then all of our subsequent snapshots are going to come in that kind of hot state of our application. So what that looks like in terms of performance, I built a pretty simple Spring Boot application and ran it through a basic artillery test. So just running a Spring Boot MVC style application with no snap start, got me kind of, I did some stuff to optimize it, right-sized it, was kind of relatively sensible, and it's kind of hello worldy. It's still 6 seconds on the cold start, so pretty painful. The warm starts are awesome, like 8 milliseconds warm start. Java is super fast at runtime, as faster than Python and Node and everything else. Pretty much up there with Rust. So I implemented snap start, just put on the switch in my IAC to switch on snap start. It got me to kind of 2.6 seconds. So a pretty big lift, but not my kind of sub-seconds that I wanted to get to. I then put in some database priming, so I made some calls to some of the SDKs that I'm going to call. That got me down to 1 and a bit seconds, still not sub-seconds. Then I ran a long-running test, and I mentioned that actually we're pulling these snapshots out of a cache. It's a tiered cache. There's a whole bunch of hosts in the Lambda fleet. Some of those caches are on the host that runs Lambda. Actually, you need to do some work to kind of prime those caches. So as I've started to run this, and I've done a whole bunch of tests, I then took a sample of the last 100 cold starts out of about 10,000 cold starts. And once you're actually running in production, then I'm getting to that kind of sub-second level. So there is a little bit of work to do. It's certainly not a pile of, not as much work as lots of other things. And hopefully we're going to see now, great. We should have seen, great, we've gone.
Yeah, how did Q do?
Q's gone and it's added on snapstart configuration in SAM, which is great. It's put it on published versions, which you need to do. It's created a function priming component, which we've got in here. We can see our priming component here is making a database call, so it's just doing a find all on the repository, so it's going and exercising those code paths. It's doing something nice and idempotent, so it's not writing anything. That's pretty neat. And it's making some suggestions of some other stuff that we can do to continue to optimize and giving us some information. So actually a pretty simple prompt, and it's done a pretty decent job of going and implementing that.
Nice. Yeah, so enabling snap start, why not, right? Cool. Okay, thanks for walking us through snap start and reducing cold starts. We got a couple minutes left. I want to talk for just a couple minutes about kind of one of the newer areas of portability that is becoming more important is AI portability. How do we take our AI workloads and have those same benefits that we talked about earlier for AI portability? And I have just a quick little demo to show here, which I'll open up. Is this one. So there's a few different elements of portability that we can talk about here that I want to show. The first one is that Spring AI is great because they've created these high-level abstractions around a lot of the things that we need in AI. So whether it's chat models, embedding models, RAG, now there's just this nice Spring API that gives us the ability to do that across different models, across different providers, that sort of thing. And so in this little demo application, I'm creating a chat client, and that chat client then needs an AI model to run on. But I can easily, through dependencies and configuration, swap out the actual LLM underneath this for different models. I can use Ollama. Locally, I can use Bedrock is the Amazon one that I'll show you. But here we have our basic chat app where I'm going to send a prompt to the LLM, say, tell me a joke. And that's it for this thing. Really nice high-level abstraction. Real quick on the configuration side, there's a couple things we need to configure. First, we need to say that we're going to use the Bedrock Converse API. That's if you go to start.spring.io, you can specify Bedrock Converse and then enable it. And that's just as an API for talking to Bedrock models. On Bedrock, there's a bunch of different models. I'm using the Amazon Nova Lite 1.0. I'll show you real quick here in the model catalog for Bedrock. You can go in and see you can use Claude, lots of different Claude models, tons of different models that are available. You can enable them. And then all you need to do is set that to be corresponding to the model that you want to use. Because this is a CLI application, I say, hey, I'm not going to start up a web application, but let's go run this thing and see if it works, see if that works. So we've got those kind of different layers of abstractions, the chat API and Spring AI being one layer of abstraction over models, and then Bedrock also adding a layer of abstraction across the different LLM providers. But there we go. Here's our joke. Why did the Scarecrow win an award? Because he was outstanding in his field. So thank you, Nova Lite model, for that wonderful joke. And so there we go. That's just your quick overview on some of the portability options. But Spring AI does a great job of doing that, and then Bedrock for different LLMs, hosted LLM models. Okay, that is all that I wanted to show on that. Let's wrap it up here. We have a great workshop if you want to dive deeper into some of the stuff we've gone through. It's called Java on AWS. And I don't know, I need to probably take that workshop. That would be good for me to go through at some point. So I don't even know what's in there. What's in there?
Yeah, it's got Lambda, Kubernetes, ECS, it's got all the stuff around how do you optimize, which kind of configuration parameters, what compiler parameters you should have. They take you through a great journey of how to bring an application to any of the umpteen ways you've got to run Java on AWS.
Awesome. Okay, well, we are out of time. I'll be around if we have other questions, but thank you. Hopefully that was useful, and thank you, Matthew, for joining me. Thanks.
Excellent.